Hey everyone, we are back again, fresh here to depress you right after holidays. And in my case, several days of only having power for part of the day. We have a nice article on the electricity demand and grid impacts of AI data centers, challenges, and prospects. And I will try not to be too haterade on, let's take care of grid. Anyway, this is by Chen, Xiaoyang Wang, Anna Colisile, Matt Lee, and Li Zi. And I'm going to skip the abstract because we are just going to get right into it. Introduction. In recent years, the accelerated advancement of generative AI, particularly large language models such as GPT, Llama, and Gemini, has fueled explosive growth in the AI industry. This surge is driving rapid expansion of data center infrastructure and imposing the unprecedented pressure on the power grid due to the immense electricity demands of ultra-scale AI workloads. For instance, training GPT-3 is estimated to have consumed 1.29 gigawatt hours of electricity, whereas the electricity consumption for training the larger scale GPT-4 rose dramatically to an estimated over 50 gigawatt hours, equivalent to nearly 0.1% of New York City's annual electricity use. According to a recent International Energy Agency report, global data centers consumed around 415 terawatt hours of electricity in 2024, about 1.5% of total global demand. And their consumption is projected to more than double by 2030 to around 945 terawatt hours, with AI identified as the primary driver of this growth. Yay! AI data centers are the computing facilities designed and optimized to execute large-scale AI workloads such as training and inference of LLMs, computer vision systems, and other compute-intensive AI applications. In contrast to traditional data centers, which primarily provide general-purpose information technology services, AI data centers are architected I should have said constructed. Okay, sorry, I'm stuck. To deliver the extreme computational performance required for advanced AI workloads, see Table 1. This capability is enabled by dense configurations of high-performance computing hardware such as graphic processing units and tensor processing units, together with high-efficiency cooling systems. Modern-scale hyperscale AI data centers typically operate with power demands exceeding 100 megawatts, and some new campuses are planned to scale to the gigawatt level. As a result, AI data centers are emerging as prominent large electric loads in the power grid with distinct characteristics and demand patterns, including high power density. Intensive AI workloads require substantially more power than conventional IT services. For instance, a ChatGPT query is estimated to consume about 2.9 watt hours, nearly 10 times the 0.3 watt hours of a regular Google search. In contrast to traditional server racks, typically operating at 7 to 10 kilowatts, AI computing racks can reach power densities of 30 to 100 plus kilowatts per rack. Such extreme power density places considerable strain on data center architecture, cooling systems, and power grids. Yeah, that's the part I'm worried about, because we don't even have enough good power grid in America to plug in all these cars you guys want to move on to it. Fast and large variability. Across the training, fine-tuning, and inference phases, AI workloads can be highly variable and bursty, with power demand fluctuating sharply over very short timescales and remaining difficult to forecast. For example, large-scale GPU clusters can produce power fluctuations of hundreds of megawatts within only seconds, bringing significant challenges for system balancing and reliable grid operation. Yeah, see, I've heard the opposite. It's like, it's going to be stable because they're just big data centers, unlike people turning their air conditioners on. But I was kind of like, no, because we might have a high peak demand. Like, okay. It never made sense to me. Grid interface via power electronics. AI data centers interface with the power grid primarily through power electronic converters, which exhibit fundamentally different dynamic behaviors from conventional electromechanical loads such as low inertia, fast response dynamics, and harmonic distortions. At scale, power electronics-based AI computing loads can pose major threats to grid stability and cause severe power quality issues. Geographic concentration. AI data centers tend to cluster in regions with low electricity prices, ample land and water resources, and favorable policy environments. That's why I want to kick them out of Michigan. In the U.S., for example, 15 states, most notably Virginia, Texas, and California, account for about 80% of total data center demand in 2023. Such concentration effect further intensifies local grid stress, and many regional grids cannot accommodate large-scale integration of data centers without substantial infrastructure upgrades. As such, rapid expansion of AI data centers poses unprecedented challenges to modern power systems. To sustain a fast pace of AI innovation and continued growth of AI infrastructure, is essential to establish a deep understanding of AI data center loads and their interactions with the grid, and to develop effective solution strategies that ensure a reliable and sustainable power system operation. A growing number of recent articles and reports have drawn considerable attention to the surging electricity demand of AI data centers and their implications for the power sector. Prior works examined the energy use of AI data centers by analyzing power consumption of key components, including AI computing, cooling systems, auxiliary facilities, and present strategies for energy-efficient operation. Reference proposes a benchmarking framework for quantifying the footprint of energy, water, and carbon emissions of LLM inference workloads. Recent study analyzes the transient dynamic behaviors of AI computing power consumption, develops high-level mathematical models for AI data center loads, and discusses the resulting disruptions and opportunities for power systems. Case studies on several power grids are conducted to assess their capacity to accommodate projected 5-year AI data center load growth, deriving implications for long-term grid planning and management. However, the existing literature is mainly focused on AI data center itself and present high-level, preliminary, and fragmented discussions, while a comprehensive and in-depth synthesis of AI data center load characteristics and their impacts on power grids, particularly the challenges from the grid's perspective, remains lacking. To bridge this critical gap and help future research and development in the field, the paper presents a comprehensive review and vision that details the overall architecture of AI data centers, together with their load characteristics and patterns, and provides a systematic analysis of the multi-timescale and multifaceted challenges posed by the rapid growth of AI data centers to power grids, along with promising solutions for enabling their large-scale integration to the grid. Specifically, Section 2 presents an overview of AI data center infrastructure and its key components. Sounds like fun. Section 3 examines characteristics and patterns of electricity demand across AI model preparation, training, fine-tuning, and inference stages. Section 4 analyzes key challenges AI data center loads bring to power systems across 3 interrelated timescales: long-term planning and interconnection, short-term operation electricity markets, and real-time grid dynamics and stability. Other critical challenges, including cybersecurity, decarbonization, and water resources, are discussed as well. Section 5 presents potential solutions from the grid side, AI data center side, and AI end-user side to address these challenges and ensure reliable power system operation. Figure 1 visualizes critical challenges discussed in Section 4 and potential solutions introduced in Section 5. At last, conclusions are drawn in Section 6. So here's the Section 2. Overview of the AI data center. This section provides an overview of the primary components of an AI data center, including IT hardware, electrical power infrastructure, cooling systems, and other supporting facilities. A typical architecture illustrating the interconnection of these components is depicted in Figure 2. Key distinctions between AI and conventional data centers are summarized in Table 1 and detailed below. So the IT hardware infrastructure forms the computational backbone of an AI data center and encompasses the computing, storage, and networking systems which execute large-scale model training and inference, manage massive data sets, and enable high-throughput communication. So computing workloads such as LLM training and inference require high-performance computing clusters designed to execute large-scale computations efficiently. These clusters typically integrate multi-core central processing units with dense configurations of graphic processing units and TPU units, which I already forgot what that was. These processing units are housed in high-density server nodes and stacked in standardized computer racks, allowing scalable deployment, efficient power distribution, and optimized cooling. Compared with conventional data centers, AI-oriented computing facilities concentrate substantially greater processing power within each rack. While a standard rack typically uses 7 to 10 kilowatts, an AI-capable rack can demand 30 kilowatts to over 100 kilowatts, with an average of more than 60 kilowatts in dedicated AI facilities. For example, the pre-rack power of an NVIDIA's GB200, NVL36, and NVL72 servers reaches about 66 kilowatts and 120 kilowatts respectively. The substantially higher power densities pose critical challenges for power distribution and thermal management. Alright, storage. To sustain intense compute capabilities, scalable and high-performance data storage is necessitated to handle massive training datasets, intermediate model checkpoints, and inference data. Tiered storage components include the hot tier, such as non-volatile memory express, solid-state drives, arrays, provides low latency and high bandwidth to store active data for fast processing. The warm tier, such as high-capacity hard disk drives, is cost-effective for storing massive, less frequently accessed data, and the code tier stores data in tape libraries or object storage systems for long-term archiving with less access speed. I did not know we still had tape libraries. Okay, cool. In addition, distributed file systems such as Lustre and Ceph allow large-scale parallel reading and writing, while object storage is used for archiving large datasets with long durability and redundancy. Unlike conventional data centers, which balance capacity, cost, and speed, AI-optimized storage prioritizes a maximum throughput and parallel access to prevent bottlenecks in that idle, expensive GPU clusters. Networking! High-speed networking is critical to ensure massive data flow efficiently between storage systems and compute nodes during large-scale AI workloads. We'll come back to that. Networking system in an AI data center includes both intra-node interconnects such as NVIDIA NVLink for high-bandwidth GPU to GPU communication within a server, and inter-node fabric such as InfiniBand or Ethernet with RDMA over converged Ethernet for low-latency, high-throughput communication between servers and racks. Specialized network topologies, including Fat Tree, that sounds like fun, and Dragonfly architectures are adopted to optimize GPU to GPU communication in distributed training environments. In contrast, conventional data centers are usually designed for more heterogeneous workloads and general purpose traffic patterns and do not require such high bandwidth or low latency. And I'm betting this is this is table 1 and then figure 1 up here, so I'll start with table 1. Comparison between the traditional data centers and AI data centers. So primary functions, general purpose IT services versus the model training, fine-tuning, and inference. Workload patterns, stable when predictable. Dynamic, bursty, and hard to predict. Compute hardware, CPU, some GPUs, GPU, TPU, dense clusters. Rack power density, 7 to 10, mentioned earlier. 30 to over 100K, mentioned also just now. Storage, balance, performance, and capacity. Mix of hard and solid-state drives, very high throughput SSD, NVMe storage with parallel file systems. The networking, you have the standard Ethernet, and in the AI, you have your ultra-high bandwidth, low-latency interconnects, which is the InfiniBand and NVLink mentioned just now. Traditional data centers, you can do air cooling, whereas AI data centers, you want liquid cooling, direct chip-to-chip or immersion or hybrid cooling, which is why they keep trying to build them around the Great Lakes. Why I'm always so torchy about them not doing that. Facility design, optimized for mixed workloads, standard floor loading in traditional data center, whereas in AI data center, you have to optimize for high-density AI workloads, reinforced structures for heavy racks, and cooling equipment. Now to look at the figures. So, critical challenges and potential solutions for large-scale integration of AI data centers to the power grid. So, challenges here. Long-term shortage of generation supply, insufficient capacity of grid infrastructure, interconnection policy, and tariff. In the short term, stress on power dispatch and reserve scheduling, impacts on electricity market and price. And in real time, disturbance from being ride through, yeah, that's fun. Large and fast power swings and grid stability, also not a good time. Power quality issues, yeah, that's what I'm worried about. Solutions at the power grid level is co-location, co-planning, accurate AI load forecasting, advanced dynamic modeling, tailored demand response, standardization, and regulation. And you go back and forth with the AI data center, so that needs to have grid-aware operation by leveraging temporal and spatial flexibility, energy-aware AI computing and hardware design, and smart efficient cooling systems. And the data center goes back and forth to the users with energy-aware prompting and AI model selection and user flexibility and AI demand response. So, on to figure 2 over here. So, this is a typical architecture of the AI data center. The transformer voltage levels and the presented double conversion UPS system are illustrative examples. Actual configurations will vary across data centers. So, we have this backup generator, a utility grid, and the automatic transfer switch. And then this goes into this transformer. I am not the best at reading electrical diagrams, so I'm probably screwing this up. But this is a switch to go for lighting and other supporting facilities. And then this circuit goes over here with another switch for the cooling units. And then we have this uninterruptible power supply, which has this switch and a battery, and then the circuit's somehow working over there. Like I said, my electrical engineering is pretty bad. Oh my god, that's because my dad was an electrical engineer. We did the light bulb things. And then this also has a circuit over here between this and this other server over here. So this is the uninterruptible power supply on one side, and then the actual phase A, phase B, phase C. So you have three-phase power going into your server, and then that's running all of your little bits and bobs, CPU, GPU, TPU, storage and networking, and then the AI model and the data are sitting on top of all that. Yay! Clear as mud for those of us that don't work on this sort of stuff, but fun to read something different. Alright, grid power supply. AI data centers are typically connected to medium or high voltage distribution grid, while hyperscale facilities may connect directly to the transmission grid as their primary power source. Depending on the local grid infrastructure and facility scale, interconnection voltages can range from about 13.2 kilovolts for small-scale installations under 10 megawatts to 15 to 230 kilovolts for hyperscale sites exceeding 100 megawatts in the US. As illustrated in Figure 2, alternating AC power enters the facility through high-voltage switchgear and protected devices, after which it is stepped down to operational voltage levels such as 480 volts via on-site three-phase step-down transformers. Okay, I kind of understood the diagram. I feel better now. These transformers not only reduce voltage but also provide electrical isolation between the utility grid and the facility's internal power supply system, as someone who had to set up three-phase conversion for a shop. Yay! The power is then distributed through main distribution panels and power distribution units to supply IT server racks, cooling systems, and other supporting loads. For the server racks, AC power is further converted to direct current DC power via power factor correction, a rectifier, followed by a DC to DC converter for DC side voltage regulation, ensuring stable and properly weighted power delivery to the IT equipment. Additionally, large AI data centers typically employ redundant utility feeders and transformers to ensure high reliability and continued operation even during partial grid outages. Yeah, that's pretty smart. The uninterruptible power supply, the UPS system, serves as the first layer of protection against power interruptions in data center operations. They provide instantaneous electrical power from energy storage devices such as batteries or flywheels when the grid supply is disrupted, ensuring continuous operation during the transition period before backup generators start and synchronize with the load. UPS deployments commonly employ battery technologies such as valve-regulated lead acid, lithium ion, and emerging solid-state chemistries. Selection criteria include specific power and energy ratings, cycle life, energy density, thermal management requirements, and cost effectiveness. UPS systems typically operate in three modes: normal mode, double conversion mode, and battery mode, and they are sized to handle high power demands of dense GPU and TPU racks and AI data centers. Modern UPS systems can also support grid interactive capabilities, enabling data centers to shift loads or participate in demand response programs by temporarily supplying power from their stored energy. Backup generation. Backup generation provides emergency power to ensure AI workloads remain uninterrupted in the event of a grid outage. Traditionally, diesel generators have been the most common solution because of low cost and their ability to quickly deliver large amounts of power to reliably support full critical IT load and essential cooling systems. To enhance sustainability, some facilities integrate on-site renewables, such as solar photovoltaic arrays or hydrogen fuel cell systems to supplement or partially replace diesel generators. Yeah, because making everything go back to the burning of petroleum products is, real environmentally friendly. We've just gone in a circle. For instance, Caterpillar and Microsoft successfully used hydrogen fuel cells to supply backup power to a data center for 48 hours. These clean generations can operate in parallel with conventional generators during outages and supply power under normal conditions to reduce reliance on the grid. Most backup generation systems are equipped with automatic transfer switches, enabling them to start within seconds and seamlessly supply power during an outage. So the cooling facilities. In AI data centers, cooling facilities are essential for dissipating substantial heat generated by high-density computing equipment, particularly GPUs and TPU-based clusters, maintaining safe operation and preventing hardware failures. A variety of cooling technologies have been used in data centers, which are broadly classified into three main categories. Air cooling circulates chilled air to absorb heat from IT equipment and expel it from the facility. Due to its low cost and operational simplicity, air cooling has been the mainstream choice for data centers with low power rack densities, below 20 kilowatts, but it becomes inadequate for AI clusters with a much higher rack power densities. Liquid cooling uses a liquid medium to remove heat from servers, which absorbs heat far more efficiently than air and allows for a very high rack power densities. For example, liquid immersion cooling submerges servers in engineered dielectric fluids, enabling safe direct contact with electric components and highly efficient heat removal. Direct-to-chip liquid cooling circulates coolant through cold plates mounted directly on processors with their high heat components, improving heat transfer without immersing the entire server in liquid. Hybrid cooling combines combines air and liquid cooling methods to optimize efficiency under varying workloads, and this approach offers flexible operation, reduces energy consumption, and mitigates the high infrastructure costs and complexity of fully liquid-cooled designs. The commonly used cooling methods are summarized in Table 3. In practice, cooling selection depends on factors such as reactor power density, energy efficiency targets, facility design constraints, capital and operational costs, and water availability. Particularly rapidly growing AI workloads are accelerating the adoption of advanced liquid-based and intelligent cooling solutions. Further discussion on smart and efficient cooling techniques is provided in Section 5b. Other supporting facilities, so beyond the core IT hardware, electrical power, infrastructure, and cooling systems, AI data centers incorporate additional supporting facilities that ensure reliable, secure, and efficient operations. These include physical infrastructure and layout, encompass data hall design features such as hot-cold aisle containment to optimize airflow, raised floors or overhead trays for organized cabling and ventilation, and structural reinforcement to accommodate weight of high-density server racks. Monitoring control systems involve dense networks of temperature, humidity, and airflow sensors integrated into the centralized building management platforms, along with fire detection and suppression systems employing inert gases or pre-action sprinklers to safeguard equipment, security and access control measures, combined physical barriers, continuous video surveillance, and multi-factor authentication to prevent unauthorized entry, and auxiliary systems comprise redundant network links, battery energy storage systems, water treatment units for cooling operations, energy-efficient emergency lighting, and dedicated office and maintenance spaces for on-site staff, because yeah, you still need humans to look at the machinery. Alright, so here's a summary of electric power infrastructure and AI data centers. So we have the component, the grid power supply, the primary electrical source is its function, your key equipment is switch and protective devices, transformers, power distribution units, and power converters. And these are connected to the 13.2 to 230 volt kilovolt grid, step down using the isolation transformers. Redundancy ensures reliability. We already talked about the uninterruptible power supply for instantaneous power during disruptions, and they're usually made of valve-regulated lead-acid, lithium-ion, solid-state batteries, and flywheels. And that's the instantaneous power supply to the backup stairs, protecting your rack, supporting grid interactive capabilities, and demand response. And then we also have backup generation, your emergency power during grid outages. These are your generators, your solar, your hydrogen fuel cells to support critical IT and cooling loads, enable seamless transition, and renewable integration. And we mentioned just now Table 3, so this is the comparison of AI data center cooling techniques. So we have air cooling, so low to moderate, simple, low cost, widely adopted. Poor efficiency for high rack power. Direct-to-chip liquid cooling is great, high, but excellent thermal transfer, ideal for dense AI workloads, but it requires plumbing, infrastructure, leaks, array risk, yes. And then there's immersion cooling, which is very high heat density sustainability, like greater than 50 kilowatts per watt. It's ultra efficient, it's low noise, it's compact. I'm guessing it's probably costly. The cons: redesign needed, fluid cost, there you go again, and specialized hardware. So that's why we're usually going hybrid cooling, medium high heat density suitability. It's flexible, it's adaptable to existing setups, and the system integration complexity is the con, because sometimes it's just easier and cheaper to start over, right? Okay, the electricity demand of AI data centers. And this section analyzes electricity demand of AI data centers. Firstly, outlines their electricity consumption, structure, and efficiency, and then presents the characteristics and patterns of the dominant component, AI computing load, across different stages of AI workflows, including model preparation, training, fine-tuning, and inference. So electricity consumption, structure, and efficiency. AI data centers are emerging as one of the fastest growing electricity consumers in the energy sector. According to the IEA report, global data centers consumed around 415 terawatt hours of electricity in 2024, accounting for about 1.5% of total global energy consumption. Looking ahead, the IEA projects the global data center electricity demand will more than double by 2030, reaching around 945 terawatt hours, with AI identified as the primary driver of this growth. The global data center electricity consumption is further discussed in Appendix A. Modern hyperscale AI facilities typically contract for power capacities exceeding 100 megawatts, with some campuses planned to scale to the gigawatt level to support ultra-scale AI training and inference. According to the Electric Power Research Institute white paper, electricity consumption in data centers is mainly attributed to IT hardware equipment, which typically accounts for 40 to 50% of total load. Cooling systems represent the second largest share, consuming approximately 30 to 40%, depending on cooling technology and server rack density. The remaining 10 to 30% is from other supporting facilities, facilities, including lighting, office spaces, monitoring, and security systems. In AI data centers, the share of electricity consumed by IT equipment is higher and typically exceeds 60% due to the adoption of high-density GPU, TPU racks, and efficient liquid cooling systems. Power usage effectiveness is the most widely used metric to measure energy efficiency of a data center, which is defined as the ratio of total facility electricity consumption over IT equipment electricity consumption being greater than or equal to 1. A lower PUE indicates greater energy efficiency with a value of 1, signifying all electricity is used for IT computation. A typical enterprise data center has a power usage effectiveness of around 1.5 to 1.6, while modern large-scale facilities achieve a lower power usage effectiveness below 1.3. For example, Google reports a comprehensive trailing 12-month power usage effectiveness of 1.9 across its large-scale data centers, and with some sites operating under 1.06. Similarly, Meta Sustainability Report states an average power usage effectiveness of 1.08 across its data centers. It indicates IT computing dominates the electricity consumption of these data centers. AI computing load patterns at different stages. Since AI computing constitutes the dominant share of electricity consumption in AI data centers, this subsection analyzes its load patterns and characteristics across the 4 main stages of AI model workflows: preparation, training, fine-tuning, and inference. So the prep stage. The preparation stage aims to prepare the AI model architecture and data before formal training begins. It includes model preparation, designing or selecting a base AI model, configuring the model size, parameters, architecture, precision settings, and conducting early phase experimental testing. Data acquisition and pre-processing. Large language models, which contain billions to hundreds of billions of parameters, require massive training data sets, often terabytes in size, that cover a broad range of content and are collected from diverse sources such as Wikipedia, Common Crawl, Bookcore, Reddit posts, GitHub codes, and other text datasets. These raw datasets must be cleaned and pre-processed into training-ready formats such as tokenization, normalization, augmentation. The extract, transform, load pipelines, my favorite, often rely on distributed computing clusters that consume significant electricity during a large-scale pre-processing. Well-designed AI models and carefully processed data are critical to model training efficiency. Empirical results show that data-centric approaches, such as removing redundant samples from datasets, performing effective feature selection, can drastically reduce the energy consumption of model training by more than 90%, underscoring the importance of developing green AI. What a concept. I don't know what else we have to do to get green AI, but I'm listening. Nevertheless, the preparation stage is flexible and widely dispersed, with workloads varying substantially depending on factors such as the choice of data processing libraries and tools, the deployment environment, and the workflow structure, making its electricity consumption difficult to quantify precisely. The training stage. The training stage is the most electricity-intensive phase of AI development, particularly for large language models. During this process, the computing hardware operates at near peak capacity for extended periods, which often runs continuously for days or weeks, resulting in significant and sustained power draw. For example, training GPT-3 is estimated to have consumed 1.29 gigawatt hours of electricity. This intensive process involved approximately 14.8 days of a continuous computation on 10,000 NVIDIA V100 GPUs in a Microsoft data center. Furthermore, training GPT-4 required an estimated over 50 gigawatt hours of electricity, approximately 40 times more than GPT-3, and equivalent to nearly 0.02% of California's annual electricity consumption. Similar LLMs, such as Meta's Llama series and Google's Gemini, require tens of thousands of high-performance GPUs operating in parallel for training, resulting in exceptionally high electricity consumption, often ranging from hundreds to thousands of megawatt hours. Typical electricity load patterns during the training stage include the initial load of the ramp-up phase. At the beginning of training, resource utilization gradually increases as data sets are loaded into memory and distributed across computing nodes, creating a short period of escalating demand. Constant high demand, computing hardware operating near maximum utilization for prolonged periods of very high power load throughout the training stage. Rapid and large power fluctuations, alternation between a power-intensive computation phase and a less power-demanding communication phase in the training stage, often leads to large power swings. Besides, tasks such as checkpointing, immediate result saving, and large-scale data transfers between nodes can cause brief but pronounced spikes in electricity consumption. Additional transient surges may occur when training is paused and resumed. High cooling load, sustained full power operation of GPUs and supporting equipment produces substantial heat, requiring cooling systems to operate at elevated capacity, which significantly increases total energy use. Electricity consumption during the training stage is affected by many factors such as AI model architecture and training configuration choices such as batch size and numerical precision requirements. Several strategies have been proposed to improve training efficiency. For example, reference showed that power capping, which limits the maximum power a GPU can consume, enables a 15% decrease in energy usage with a marginal increase in overall computation time. Other approaches include dynamically adjusting training parameters based on convergence progress and implementing early stopping when performance improvements plateau. And the fine-tuning stage adapts a pre-trained AI model to a specific downstream task, such as a large legal text analysis, medical report summarization, or customer service chatbots. Since the AI model has already undergone extensive pre-training, fine-tuning typically requires substantially less computation and electricity than training from scratch. Empirical measurements show that pre-training BERT consumes electricity equivalent to approximately 400 to 45,000 fine-tuning runs, depending on dataset size and task complexity. Nevertheless, as fine-tuning often involves smaller datasets, frequent evaluation cycles, and hyperparameter tuning, power use tends to be more variable. Rather than maintaining a sustained high baseline, fine-tuning workloads typically exhibit intermittent bursts of GPU utilization, followed by lower activity periods. Typical electricity use patterns during fine-tuning include moderate average demand, generally lower than full pre-training, but varying by model size and dataset. Bursty workloads with short periods of high consumption during forward-backward passes, validation, hyperparameter exploration, and cooling demand variability, with cooling loads fluctuating in step with computational bursts. Although a single fine-tuning run consumes far less energy than pre-training, its much higher frequency across numerous organizations implies that fine-tuning can cumulatively represent a non-negotiable share of total lifecycle energy consumption, underscoring the need to enhance its efficiency. For example, reference introduced Green Trainer, an adaptive fine-tuning algorithm that strategically selects which model parameters to update. This method reduces fine-tuning workload by up to 64% with significant accuracy loss, highlighting the potential to make fine-tuning more energy efficient. Reference analyzes the trade-off between energy consumption and model performance, showing fine-tuning smaller models such as T5-base, BART-base, or Llama 3-8B can achieve competitive results while significantly reducing energy usage. Inference stage. Inference is the process of executing a well-trained AI model to generate outputs in response to user inputs. On a per-query basis, the least energy-intensive stage of the AI model lifecycle. Nevertheless, as inference is performed continuously at scale, often serving millions or billions of requests, its cumulative electricity consumption can exceed that of training. Compared to 40% for training, inference represents about 60% of total AI energy usage at Google, owing to the billion user services that rely on AI. Recent estimates suggest inference can account for up to 90% of a model's total lifecycle energy use. The electricity consumption for a single AI inference query varies widely depending on model size and architecture, prompt length, and task complexity. Compared to a traditional Google search, which consumes about 0.3 watt-hours, a recent study estimates that GPT-03 consumes 39.2 watt-hours, DeepSeek R1 33.6 watt-hours, and GPT-4.5 at 30.5 watt-hours for processing a long prompt query, whereas GPT-4.1 Nano requires only 0.45 watt-hours. Reference compares inference energy consumption across a wide range of tasks and shows that image generation is among the most energy-intensive, whereas simpler tasks such as text classification consume significantly less electricity. Not that surprising. Unlike the sustained high-load profile of model training, inference workloads are characterized by significant variability, and this is driven by fluctuating user requests, diverse query complexities, and the unpredictable nature of real-time interactions, resulting in short, intense bursts of computing load. As a result, typical electricity use patterns in the inference stage include low average demand per query, but high total demand over time due to continuous operation, bursty and unpredictable spikes in user activity and varying task complexity, and strong diurnal patterns with peak usage during business or social activity hours. Supporting such dynamic loads necessitates scalable and flexible IT and power infrastructure capable of rapidly adjusting resources to provide fast response and maintain operational reliability. Energy efficiency can be improved at both the hardware and software level. Specialized low-power accelerators such as FPGAs and ASICs can reduce energy consumption, while techniques like model quantization, pruning, and knowledge distillation further enhance performance. Emerging architectures such as retrieval-augmented generation introduce additional computational complexity by combining model inference with large-scale data retrieval processes. Despite the exponential growth in model parameters, the associated energy cost of inference has been shown to grow sublinearly, suggesting that efficiency gains can partially offset the demands of larger architectures. That's kind of good. So figure 3, an illustration of the patterns of AI computing load represented by GPU power during training, fine-tuning, and inference stages. Data derivative refer to figures 9, 13, 15, and table 3 for detailed data and experimental settings. Alright, so a little summary and discussion of this section. AI computing load is highly energy intensive, with each stage of the workflow contributing differently to the total electricity consumption. According to the inference stage, it represents a dominant share of approximately 60% of the energy footprint, while training accounts for 30%, and model preparation and fine-tuning make up the remaining 10%. Moreover, these stages exhibit distinct load patterns. Figure 3 illustrates the typical time-varying electronic computing load as measured by GPU power patterns across different stages of the AI workflow, excluding the data preparation stage due to its typically dispersed energy usage. The electricity load estimates for each stage are derived from where the tasks were executed using GPT-2. Additional experimental details are available as shown in Figure 3. All stages exhibit an initial rapid ramp-up phase, during which power consumption rises sharply from a low near zero value to a high operational level. In the training stage, power remains consistently high. Oh, I blinked and it moved. Okay, characterized by intermittent large rapid load fluctuations, along with persistent high frequency, small scale variations, the magnitude of which depends on the underlying hardware and training algorithms. The fine-tuning stage begins with pronounced high frequency, large magnitude fluctuations, which gradually decrease in frequency over time. However, moderate fluctuations continue throughout the process. In contrast, the inference stage operates over much shorter durations and exhibits highly variable short bursts of power demand, driven by the stochastic nature of real-time inference requests. This diversity in load profiles underscores critical need for advanced AI data center designs, grid integration strategies, and power-aware workload scheduling approaches that balance performance, sustainability, and system reliability. Oh my gosh, we're already 36 minutes in, and I'm not even... Well, no, I guess I am to halfway. I'm going to finish reading, but I do need another pause to stretch my back. So what are the grid impacts and emerging challenges of AI data centers? The rapid expansion of large-scale AI data centers is imposing unprecedented demands on electric power grids. With immense electricity consumption subject to large and fast fluctuations, these facilities introduce emerging impacts and operational challenges for power grids. This section analyzes these challenges across 3 interrelated timescales, including long-term planning and interconnection, short-term operation market, and real-time grid dynamics and stability, illustrating how AI data center loads affect each phase of power grid management. Other critical challenges, such as cybersecurity, decarbonization, and water resources, very important, are discussed as well. So in this case, like we saw in the diagram, it starts from the long scale and goes to the short scale. So over the long-term time scales, years to decades, AI data centers are projected to drive a sustained increase in electricity demand, requiring substantial investment in generation capability, transmission infrastructure, and distribution equipment in order to maintain an adequate and reliable electricity supply. According to the IEA report, global electricity consumption by data centers is projected to more than double by 2030, reaching approximately 945 terawatt hours. We repeat ourselves a lot in this article. With AI workloads expected to be the primary driver of this growth. However, many regional grids are incapable of accommodating large-scale data centers without extensive transmission and distribution upgrades, which often require 5 to 10 years for planning, permitting, and construction. Yeah, stuff ain't easy. Reference: assess the 5-year projections of AI data center demand across several bulk power grids and found resource adequacy constraints could severely limit their planned growth, particularly in high-density clusters such as Algrid in Ireland, Dominion in the US. Moreover, AI data centers tend to concentrate in a limited number of regions, driven by low energy prices, available land and water, Michigan, and supportive policy environments. Hopefully not Michigan. For example, in the US, 15 states, notably Virginia, Texas, and California, account for an estimated 80% of the national data center load in 2023, as shown in Figure 4. This geographical concentration effect further intensifies regional grid stress. Yes, you guys on the West Coast, you down in Texas, and for whatever reason Virginia. Well, I don't know, maybe that's because of DC. Anyway, y'all using all the power, knocking off. To address this challenge, coordinated co-planning of AI data centers, the power grid, and generations can reduce costly infrastructure investments, alleviate transmission congestion, enhance operational reliability, and support decarbonization goals. This approach integrates transmission, distribution, expansion planning with strategic siting of AI data centers, as well as the optimal siting and sizing of additional generation and energy storage resources. A number of studies focus on the modeling and optimization of joint planning for conventional data centers on the power grid, with solutions tailored to AI data centers remain largely underexplored. Another key strategy is co-location with dedicated local generation, such as renewable generators and nuclear power plants. This scheme can directly supply large stable power sources to high-demand AI workloads, reducing reliance on long-distance electricity transmission and mitigating grid integration challenges. And I find this kind of funny because one of the reasons we ended up with alternating current is because it could go long distances without losing its actual power, whereas direct current couldn't. And now we're thinking about like inverting the whole structure that Thomas Edison was advocating for in the first place, which was like local power generation and distribution, and that way you could like cover yourself and then, have backup if you need backup from somebody nearby. But yeah, this just cracks me up. We'll move to a centralized and then decentralized, then we move back again, and isn't history fun? We just keep flip-flopping back and forth on the pendulum. Alright, for example, Amazon Web Services arranged to source approximately 960 megawatts directly from a nuclear power plant in Pennsylvania to power its data center under a dedicated power purchase agreement. Google and Kairos Power have signed a master plant development agreement to deploy a fleet of advanced small modular reactors to produce up to 500 megawatt of clean electricity to Google's AI data centers. In addition, the grid interconnection policies and regulatory frameworks remain among the most significant bottlenecks for AI data center deployment. For example, in 2025, Texas passed State Bill 6, which redefines the interconnection process for large electrical loads, such as data centers exceeding 75 megawatts within the ERCO grid. Under this bill, large load customers must submit interconnection requests to the interconnecting utility and comply with new requirements, including disclosure of similar requests, reporting of on-site backup generation, payment of a minimum of 100K transmission screening study fee. Okay, yeah, you're just jacking people there, Texas. Proof of site control and a financial commitment to cover transmission infrastructure costs. Oh, wow. Complex regulatory and permitting workflows, thorough grid integration studies, overloaded interconnection queues, and the need for major grid infrastructure upgrades are causing multi-year delays in data center deployments across regions, such as Northern Virginia, refining interconnection processes and deploying AI and automation tools to accelerate interconnection studies could significantly reduce these delays. Moreover, tariff structure varies across jurisdictions, and many data centers fall under smaller regional utilities and are subject to distribution level tariffs. Fun. While hyperscale facilities connect directly to bulk transmission systems, exposing them to world-scale market price signals. As a result, tariff design standardization are crucial to ensuring cost predictability and sustaining the deployment of AI data centers. Yeah, and we got the guy that likes to monkey with the whole tariff policy right now. Anyway, with my thoughts on that aside. Short-term operation electricity markets. The short-term timescales, hourly to weekly, the large-scale integration of AI data center loads ranging from tens of hundreds of megawatts introduces substantial operational and market challenges to the power grid. So the impacts on dispatch and reserve scheduling and maintaining balance between generation and demand is a fundamental objective of power system operation. Otherwise, it all goes belly up. On the short-term timescale, power balance is achieved through unit commitment and economic dispatch supported by reserve scheduling to accommodate unforeseen power variations. The immense and bursty power usage of AI data centers, particularly during intensive model training and large-scale inference, introduces significant uncertainty and rapid load variations to the grid operation. These challenges conventional deterministic power dispatch schemes and necessitates advanced short-term forecasting techniques for AI data center loads. However, accurate prediction remains inherently difficult due to their complex non-cyclic patterns and dynamic scheduling behaviors of AI workloads. In addition, the rapid and unpredictable ramping of AI data center loads imposes greater reserve requirements to ensure reliability amid large and fast load variations. Grid operators need to maintain elevated spinning and non-spinning reserve margins, which increase operational costs and call for additional fast-responding reserve resources. And who's going to pay for that? Is it the company running the AI, or is it all your consumers? Impacts on electricity market and price. Large-scale AI data center loads are expected to place upward pressure on capacity market clearing prices as higher peak demands require additional capacity commitments. Yeah, so not only will you not be able to run your air conditioning during peak hours, you might not be able to have any power at all because everyone needs to query Gemini about stuff. Anyway. This impact has been observed in PJM, where the capacity market clearing prices for the 26-27 delivery year increased to $329.17 per megawatt, over 10 times higher than the price of $29.92 per megawatt in the 24-25 delivery year, with rapid data center growth identified as a major contributing factor. Yeah, I don't want to be paying that. Similar effects are emerging in New York ISO and ERCOT, where anticipated data center expansion is influencing forward capacity markets and resource adequacy planning. Okay, Deja, get your generator now. In addition, the substantial and often unpredictable demand from AI data centers raises marginal generation costs in wholesale markets as more expensive mid-merit and peaking units are dispatched to meet AI-driven loads. It also amplifies price volatility in day-ahead and real-time markets due to short-term large AI load fluctuations. Rapid AI load surges can result in sharp increases in locational marginal prices, particularly in transmission congested areas. So we're going to get surge pricing for electricity. That'll be fun. So like during peak times, like not only can you not call people unless you want to pay full long distance prices, now you'll have to like turn off your power when you get home from work, because everyone's gonna want to watch TV or do your tablet at the same time, and that's not gonna work. Oh. Yeah, I don't think we should get rid of the internal combustion engine for cars quite right now because we're going to plug all that in and then we're going to try to run the AI on top of that and they're going to do surge pricing to us? Why? Oh, okay. Real-time dynamics and grid stability. So in real-time and fast time scale, sub-seconds to minutes, large-scale AI data center loads can significantly impact power system dynamics and stability. These facilities are inherently power electronic-based loads with their dynamic behavior governed by the control of internal power electronic converters but used by the computational workload scheduling dynamics. So grid disturbances ride through. AI data centers interface with the power grid through high-capacity power electronic converters, which are sensitive to short-duration voltage and frequency disturbances at the point of interconnections, such as voltage sags, voltage dips, and the upward or downward frequency deviations. These disturbances can induce substantial power oscillations and even trigger the disconnection of an AI data center from the grid to protect internal electronic devices. Without adequate fault ride-through capabilities or grid disturbance tolerance measures, sudden trips can occur during grid faults, potentially exacerbating the original grid disturbance. In regions with high concentrations of AI data centers, simultaneous tripping events can take place and lead to cascading outages. Fun! These impacts have been observed in practice. For example, high-frequency, undamped power oscillations appeared in a data center-rich region in Dominion Energy's grid, triggered by a once-a-second voltage sag. ERCO has also reported multiple events wherein large computing loads tripped during transmission faults due to insufficient ride-through capability. For example, Figure 5 illustrates the grid frequency dynamics under several large electronic load trip events studied in ERCO. It shows that the loss of more than 2,600 megawatts of such loads can drive system frequency up to 60.4 hertz, a level at which conventional generators may fail to ride through, potentially leading to uncontrolled cascading events. To this end, ERCO considered imposing ride-through requirements for large data center and crypto mining loads to ensure reliable interconnection and grid operation. Yeah, that sounds like fun. Let's put everything in the robot's hands and watch it all burn. Yeah. Power fluctuations and grid stability. AI data centers can introduce rapid power fluctuations during cold starts, planned shutdowns, workload transitions, or sudden load interruptions triggered by faults or operational contingencies. For example, training large-scale AI models across tens of thousands of GPUs can induce significant power swings, arising from the synchronous nature of these jobs and the alternation between a power-intensive computation phase and a less power-demanding communication phase. In addition, inference workloads often exhibit rapid start-stop behavior with sharp spikes followed by sudden drops in power consumption, as shown in Figure 3. Unlike conventional electrical mechanical loads, power electronics-based AI data center demand may change by tens to hundreds of megawatts within sub-second intervals, posing substantial stability risk to the power grid. Such abrupt power variations can challenge the grid's frequency stability, induce voltage excursions, and interact with the dynamics of grid-connected generation and control systems. Such abrupt power variations can challenge the grid's frequency stability, induce voltage excursions, and interact with the dynamics of grid-connected generation and control systems, potentially exciting oscillations and instability. And yes, if I just read this sentence a second time in a row, I apologize. I had to pause for the exciting and get the heck out of the building announcement. For instance, a major resonance event was reported in 2017 across multiple Facebook data centers and analyzed in, as noted in, unlike solar plants and wind farms, data centers typically have internal impedances much higher than those of transmission lines or distribution transformers, which can amplify such resonance phenomena. From a data center perspective, reference proposes three classes of power stabilization techniques to mitigate large power swings, including software-based methods that inject controlled workloads to smooth power transitions, GPU-level firmware mechanisms that enforce ramping constraints and power floors, and rack-level energy storage systems to reduce fluctuations by absorbing and releasing power as needed. Beyond these approaches, addressing the challenge of large power fluctuations also requires accurate dynamic modeling of AI data center behavior and close coordination between grid operators and data center operators to ensure effective mitigation and maintain system-level stability. Moreover, as data centers typically employ fast-acting UPS systems for power continuity, transitions between grid supply and UPS operation during disturbances must be carefully managed to prevent large transient power swings or synchronization issues upon reconnection. Power quality issues. High-frequency switching devices and power electronic equipment in data centers can introduce significant harmonic distortions to the grid, degrading local power quality and posing risk to nearby electrical facilities. These distortions originate primarily from nonlinear power supplies, AC-DC conversions, and the control server PFC circuits. In large-scale AI facilities where thousands of server racks operate simultaneously, these harmonics can accumulate and propagate into the local distribution system, presenting risk to industrial and residential equipment such as malfunctions, accelerated wear, overheating, and electrical fires. Oh, goody gumdrops. You're going to set my house on fire, too. According to a 2004 Bloomberg analysis, sensor data from more than 70,000 homes reveal a strong correlation between proximity to data centers and declining power quality, with evident effects observed within 20 miles of major data center clusters. Holy smokes. If you are near one of these things or where one of these things is getting built, leave the heck out of there. I did not know that. It's going to be pretty mind-blowing when I finally post this next week. All right. Beyond harmonic distortion, AI data centers may contribute to other power quality issues, such as voltage flicker during rapid load changes. I've been experiencing that lately. Real annoying, because I wonder if it's going to, like, burn out my freaking appliances, because, yeah, it happened a lot when stuff was getting turned back on. Unbalanced loads across three phases, interharmonics, are caused by certain switching patterns in high-frequency converters. These power quality issues can propagate through the grid, goody gumdrops, potentially degrading protection system performance, reducing metering accuracy, ooh, even better, shortening equipment lifespans, breaking my appliances just like I thought, and impairing control system stability. To mitigate power quality issues and maintain compliance with industry standards such as the IEEE Standard 519-2014, key approaches include active harmonic filtering at the AI data center facilities, phase balancing and load redistribution to minimize neutral current distortion, coordination with grid operators for harmonic monitoring and mitigation planning. Please tell me we're doing that. UPS and converter design optimization to minimize harmonic generation at the source. As AI data center capacity keeps expanding, proactive power quality management will be critical for maintaining grid stability and ensuring equipment safety and regulatory compliance. Other critical challenges. This subsection discusses other critical challenges arising from rapid expansion of AI data centers, including cybersecurity, decarbonization, and water resources, my personal favorite. So, cybersecurity. AI data centers not only present major physical impacts on the power grid as discussed above, but also introduce emerging cybersecurity risks to power systems, which already really don't need that. Their highly concentrated electricity demand, dependence on programmable power electronics, and integration with cloud-based control architectures collectively increase the vulnerability of power systems to cyber attacks. Yeah, that's one of the pluses of, like, some of the very old COBOL-based things that, like, run nuclear reactors, is they're so, arcane and off the central grid that they're really hard to attack. You don't want people taking down your nuclear reactor, right? And in this case, you're going to connect stuff more to the grid and more to the network, which not necessarily a good idea with utilities like power. Yeah. Specifically, coordinated cyber intrusions can manipulate workload scheduling or UPS switching, deliberately inducing sudden surges or drops of hundreds of megawatts in power demand. China, are you listening? And such abrupt load changes pose a significant threat to grid stability, potentially overloading local distribution networks and disrupting frequency regulation and triggering cascading failures across interconnected systems. Oh, we could do this during an election year. That would be amazing, wouldn't it? For instance, in 2024, a large-scale disconnection event occurred in Virginia's data center alley, where a protection system failure caused 60 out of more than 200 data centers to suddenly disconnect from the grid and transition to on-site generation. This abrupt loss of load introduced a significant power imbalance, compelling the utility to rapidly curtail generation in order to avert cascading outages. Although the event was not triggered by malicious cyber attacks, it underscores how sudden shifts in data center loads can impose substantial stress on grid stability. This doesn't quite make much sense to me, but maybe one of you guys can explain in the comments, because it's like the big power center disconnected it, and so the rest of the grid had like too much power running on it. Is that like why it had to? Yeah, because otherwise you'd be generating power and putting too much power into the grid that couldn't hold it. At least that's my theory. Please feel free to put in the comments whether or not you think I'm right, because that's kind of sort of how I'm understanding that. Like there was too much power, and then they had to like stop generating power in the central location because nobody else was taking it up, and then you get a fire or something, right? Okay. Just trying to make sure I understand things in my slow little way. Alright, beyond transient disturbances, maliciously orchestrated or malfunction-induced workload patterns can act as sources of forced oscillations, periodically modulating AI data center demand in ways that resonate with the grid's natural modes. Such oscillatory injections can amplify inter-area oscillations, reduce damping margins, and in extreme cases trigger widespread instability. Unlike conventional industrial loads, the inherent controllability and programmability of AI workloads render them particularly susceptible to being exploited as virtual power perturbation sources. There's a word we don't always get to hear every day, perturbation. This tight coupling between cyber-level control and physical load response highlights the urgent need for integrated approaches that jointly address cybersecurity and power system dynamics. Effective countermeasures include the implementation of secure communication protocols, the development of anomaly detection mechanisms tailored to workload-induced oscillations, and the establishment of collaborative frameworks between data center operators and grid utilities to prevent cascading failures triggered via cyber attack. Decarbonization. According to the IEA report, carbon emissions from the electricity use of global data centers reached 180 million tons in 2024 and are projected to rise to 300 million tons by 2035, raising concerns that the rapid growth of AI facilities could further exacerbate climate change. Nevertheless, AI data centers generally do not produce direct carbon emissions during normal operation, apart from on-site backup generators such as diesel units, which are only infrequently activated. Instead, AI data centers mainly account for the indirect carbon footprint associated with their electricity consumption, with the carbon emission intensities determined by generation fuel mix and electric power flow of the supplying power grid. See for a more detailed introduction. Consequently, the coupling between electricity demand and grid carbon intensity highlights the importance of considering both energy efficiency measures within AI data centers and the decarbonization trajectory of power grids. At present, data center owners achieve their decarbonization goals primarily by co-locating renewable generation with data center campuses, or through procuring renewable energy in the electricity market via power purchase agreements or renewable energy certificates. For example, Google launched its 24/7 carbon-free energy program aimed at sourcing carbon-free electricity for its data center operations on a continuous 24/7 time basis for decarbonization. Water resources! My personal favorite thing to tell people why we don't need your data center here. In Michigan, in particular, don't screw up our Great Lakes. We need our inland seas. Many large-scale data centers utilize evaporative cooling systems to dissipate heat, a process that consumes substantial volumes of water daily, often amounting to tens of thousands or even millions of liters of water, depending on facility size and climate conditions. As indicated in a report, a 100 megawatt data center in the U.S. on average consumes around 2 million liters of water per day, equivalent to about 6,500 households. It estimates that global water consumption for data centers is currently around 560 billion liters per year and could rise to around 1,200 billion liters per year in 2030. 2030. As a consequence, together with high electricity demand, substantial water withdrawals are emerging as a critical limiting factor for AI-driven data center expansion, especially during summer peaks when both water availability and power supply are under stress. I'm going to take a second to do a little bit of math here, which it might only interest me, but we are looking at, what is it, 100 megawatt data center, 2 million liters of water, so, oh geez, okay, never mind, I was thinking I could do million into billion. And I'm going to end up the joys of dyslexia and too many zeros, because I was going to be like, how many households is that? Way too many. I'm just going to drag that back over here. Feel free to do the math if you want, if you are like equally fired up, and put the answer in the comments, because, yeah, I was good until we started doing million versus billion, and I was like, too many zeros. Alright. It's the end of the day. Can you tell? Alright. According to Bloomberg, nearly 2/3 of new U.S. data centers built since 2022 are located in high water stress regions, such as the Southwest, Texas, and parts of the Midwest, some of which face growing risks of drought and water scarcity. Yes, don't come to the Great Lakes, though, because I don't want you to drain our inland seas. Reference proposes a general framework for evaluating the water impact of computing by factoring in both spatial and temporal variations in water stress. In blank, the events influencing data center water use are analyzed, such as server efficiency, server utilization, and cooling techniques. The study also finds there is no single recipe for minimizing water use. Instead, optimal outcomes depend on tailored combinations of these factors to reduce stress on water resources. Integrated planning frameworks that jointly assess electricity and water footprints of AI data centers are necessary. Effective strategies include adopting low water cooling technologies in water-scarce regions, siting facilities with attention to both water availability and grid capacity, and incorporating climate resilience measures into future AI infrastructure planning. Yeah, that siting the facilities is the issue I'm having right now, because everyone's like, let's come build it right here, because there's a whole bunch of water, and it's totally cool to screw up the big freshwater, supply we have on this continent. Because America. Potential solutions and opportunities. In addition to the approaches discussed in Section 4, this section presents further solutions and opportunities to address challenges associated with rapid integration of AI data centers, considered from 3 perspectives: power grid, data centers, and AI end users. So solutions on the power grid side: improve the forecasting of the AI load. Accurate forecasting of AI data center loads, particularly during large-scale model training and inference stages, is critical for grid planning and operation. Unlike traditional data center loads, AI workloads exhibit highly irregular temporal patterns with abrupt transition between load utilization and peak demand periods. These rapid changes can generate sharp power surges that challenge power dispatch, reserve scheduling, and real-time grid stability. Effective forecasting requires a comprehensive understanding of AI workload characteristics, including job scheduling policies, training cycle durations, hardware utilization patterns, and the interaction between compute intensity and cooling system demand. To address privacy concerns, load forecasting can be performed internally by AI data centers, while only aggregated results are reported to the grid operator. Alternatively, collaborative forecasting frameworks where AI data center operators share anonymized workload information with grid operators can be developed to enhance situational awareness and support preventive grid operations that mitigate potential impacts. As a complement, recent advances in machine learning techniques can be leveraged to enhance AI load forecasting. These approaches integrate telemetry data from IT infrastructure, job queue statistics, and environmental factors with advanced machine learning tools to predict short-term fluctuations and identify potential peak demand events before they occur. For example, hybrid statistical machine learning models have been shown to improve short-term prediction accuracy for cloud and AI computing facilities compared to traditional autoregressive models. And then we have dynamics modeling of AI data centers. High-fidelity modeling of the electrical dynamics of AI data center facilities is essential for assessing the grid disturbance ride-through capabilities and their interactions with power system stability. As inherently power electronics-based loads, AI data centers exhibit dynamic behavior governed by internal power converter controls and the temporal characteristics of computational workload processing. Hence, electromagnetic transient modeling using tools such as EMTP or PSCAD is required for capturing the fast, high-frequency responses of these AI facilities, which may not be accurately represented by conventional phasor domain models. A recent dynamic load model tailored for AI data centers is proposed that incorporates 3 key features, including an upstream UPS, cooling modes represented by induction motor dynamics, and pulsing compute loads to represent AI workload transients. Complementary approaches include hierarchical and hybrid modeling frameworks that combine high-fidelity electromagnetic transient simulations for critical components with reduced order equivalents for external network regions. This method balances computational efficiency with accuracy, enabling reliable simulation of real-world grid impacts from AI data center behavior. And then we have the tailored demand response program design. So, to effectively harness the flexibility of AI data centers while minimizing adverse operational impacts, grid operators need to design demand response programs specifically tailored to the unique characteristics of these loads. Standard price-based demand response mechanisms, while widely used in residential and industrial contexts, may introduce new challenges when applied directly to large-scale AI loads. For example, inference or training tasks deferred in response to high electricity prices may be rescheduled simultaneously once prices fall, leading to secondary demand peaks or rebound effects that stress the grid. Moreover, AI data center operators are relatively insensitive to electricity prices. As noted, in these facilities have high sunk capital costs, and the workloads they run are highly lucrative. As a result, the opportunity costs of deferring a training or inference task can outweigh potential savings from energy arbitrage. Therefore, relying on price signals alone may be insufficient to drive effective load shifting. This underscores the need for carefully designed demand response mechanisms tailored to AI data centers. One promising direction involves incentive-based or penalty-based and contract-based demand resolution mechanisms in which AI data centers commit to predefined levels of flexibility in exchange for direct compensation or priority grid services. Oh, goody gumdrops! So you'll get your AI before I get to keep my lights on. Good deal. For example, Google has signed contractual agreements with utilities in Indiana and Tennessee to curtail AI workload during periods of grid stress. Okay, so you agreed to take it down during grid stress and then you get something else out of it, I am sure. Additionally, coincident peak mechanisms such as ERCO's for coincident peak charge, which imposes significant penalties on energy consumption during the grid's 4 highest monthly demand intervals, can directly incentivize data centers to shift their usage away from peak periods. Or just screw the pores. Either way. Standardization and regulation. As the scale and concentration of AI data centers increase, the implementation of specific standards and regulatory frameworks becomes essential to confine their load behavior and preserve grid reliability. One key task is the specification of fault ride-through capabilities, similar to requirements imposed on renewable energy sources under IEEE Standard 1547 and European grid codes. AI data centers may be required to remain connected during short-term voltage or frequency disturbances. For instance, proposed specifications for data center UPS systems suggest maintaining operation down to 50 to 70% of nominal voltage, with the resynchronization capability within 1 second. In addition to ride-through, dynamic performance requirements should address acceptable voltage and frequency tolerance ranges, reactive power support, harmonic emissions, and ramp rate limits. Such performance standards are increasingly being applied to large electrical and hybrid loads under evolving European interconnection frameworks. Moreover, interconnection standards may require that AI data center operators provide utilities with accurate dynamic models, anonymized workload profiles, and operational telemetry to enable realistic system planning and stability analysis. On the regulatory front, the North American Electric Reliability Corporation has launched a large loads task force to assess and manage risks associated with high-density data center growth. There is growing momentum for applying grid codes to large sensitive electronic loads, including mandatory response characteristics during contingencies. As a result, these regulatory standardization measures are critical to ensuring that the integration of AI data center supports rather than undermines the stability and resilience of the power grid. So, solutions from the AI data center side. Leveraging temporal and spatial flexibility of AI data centers for grid-aware operation. Sounds great. Flexible AI workloads can be rescheduled or shifted without compromising service quality, offering valuable flexibility to support grid operation. Specifically, temporal flexibility refers to the ability to shift AI workloads over time without compromising service quality or user experience. For example, non-urgent computational tasks such as large-scale model training or batch inference can be scheduled during off-peak hours on periods of low grid stress and high renewable energy availability, and this helps to flatten load load curves, enhance grid utilization, lower operating costs, and reduce carbon emissions. Spatial flexibility refers to the capacity to reroute AI workloads across multiple data centers in different geographic locations. This allows AI workloads to be rerouted to facilities and regions with cleaner electricity, lower prices, or less grid congestion. Again, you're going to screw with those of us in rural areas. Thank you. Together, temporal and spatial flexibility offer powerful levers for optimizing the alignment between AI demand and power system distribution, or power system conditions, helping to enhance grid reliability, reduce carbon emissions, and lower operational costs. Oh, I think I combined 2 sentences above up there. Sorry about that. Prior research shows that temporally shifting AI workloads can reduce operational costs by up to 12% and carbon emissions by approximately 10%. Real-world implementations are increasingly supported by energy-aware scheduling platforms and demand-sensing technologies. Moreover, studies based on locational marginal emissions modeling highlight that even modest spatial shifting of loads can yield significant emission reductions. In addition, AI data centers equipped with advanced control systems and on-site energy storage can mitigate their own power fluctuations and even provide ancillary services to the grid. By modulating compute intensity or charging and discharging stored energy in response to grid signals, such facilities can contribute to frequency regulation, spinning reserves, and fast ramping support. I hope that's the case. This positions AI data centers not only as large load consumers, but also as active grid participants that can enhance grid reliability. Okay, if we go that route, I might be happy. I just don't want my power to be off. It stinks. I don't like doing Amish time. No offense to the Amish. Energy-aware AI workload and hardware. AI computing accounts for the largest share of electricity consumption in AI data centers, making advances in computing efficiency and management crucial for reducing energy footprint and stabilizing power demand. Several complementary strategies are outlined below. So energy-aware AI computing. Techniques such as energy-aware training enable models to activate only the neurons and connections necessary for a given task, effectively disabling unused components and lowering power use. Maybe that's what we do with our brains. Anyway, additional savings can be achieved through dynamic voltage and frequency scaling of CPUs and GPUs. For example, reference reports that underclocking a single NVIDIA A100 GPU for a specific application reduced power consumption by 40% while decreasing performance by only 22%. This demonstrates certain jobs could be executed at lower frequencies over a longer duration to reduce overall energy use. Moreover, advanced power smoothing and management techniques at the software and GPU levels can be developed and deployed to mitigate power swings induced by AI workloads, thus reducing risk to grid stability. Development of lighter task-specific AI models. Smaller task-specific models can match the accuracy of large foundation models while consuming substantially less power. Techniques such as priming, removing redundant parameters, quantization, reducing numerical precision, and knowledge distillation, transferring knowledge from a large model to a smaller one, lower computational demands without compromising output quality. These approaches also facilitate deployment on edge and mobile devices while yielding significant energy savings. For example, Tiny BERT achieves over 90% lower energy consumption compared to full-size BERT models. Furthermore, sparse model architectures enhance efficiency by directing computational resources toward the most critical regions of the network. And then you have your energy-efficient hardware design. The deployment of energy-efficient hardware necessary for reducing the carbon energy footprint of AI data centers. Advances in processor architecture can substantially improve performance per watt, enabling higher computational throughput and lower power costs. Domain-specific accelerators, low-power CPUs, GPUs, and AI-optimized hardware such as Google's TPUs are essential to this effort. For instance, Google's TPU version 4-based computer supercomputer has demonstrated notable speed and efficiency gains over NVIDIA A100 GPUs. Moreover, AI itself can be leveraged to optimize performance and energy efficiency of its supporting infrastructure, as illustrated in co-optimizing AI model architectures with underlying hardware. Combining techniques such as pruning, quantization, hardware-aware model design offers further potential for achieving substantial energy savings without sacrificing accuracy. And then you have smart and efficient cooling techniques. Cooling facilities account for the second largest share of electricity consumption in AI data centers. Recent research and industry trends emphasize several advanced strategies. Hybrid air-liquid cooling systems, combining air-based airflow management, such as hot and cold aisle containment, in-row cooling, raised floor systems with liquid approaches, direct-to-chip to optimize energy complexibility and adaptability. These systems help manage thermal loads from dense AI clusters while reducing energy usage compared to air-only or liquid-only designs. Immersion and direct liquid cooling, immersing servers in dielectric fluids or using piping-driven liquid heat removal offers dramatically improved heat transfer, higher rack density, and up to 50% energy savings compared to air cooling, though challenges remain around maintenance and cost. AI-driven adaptive and predictive cooling control, leveraging reinforcement learning, deep neural networks, or other machine learning models to anticipate thermal load changes and dynamically tune cooling systems for maximum efficiency. These approaches have achieved 14 to 21% energy savings in live data cluster deployments without violating safety constraints. Google's commercial cooling experiments using reinforcement learning yielded 9 to 13% energy reductions, renewable, powered, and free economizer cooling, leveraging ambient air, free cooling requirements permit. Come up north, empowering cooling infrastructure with on-site renewables such as solar and wind to reduce the carbon intensity. These approaches support sustainable operations while attenuating grid demand. These smart and efficient cooling strategies underscore a shift towards multidimensional optimization to balance energy, carbon, water, and operational complexity. So what's up next? Solutions on the AI end user side. Energy-aware prompting and AI model selection. End users and developers of AI applications can contribute to reducing the AI electricity footprint through energy-aware application development and informed usage decisions. For end users, one critical approach is the adoption of energy-efficient prompting strategies and the selection of appropriately scaled models. Recent studies have shown that longer, more verbose prompts, while potentially improving model interpretability or output alignment, can significantly increase the number of tokens to be processed and thus greatly elevate the power consumption of LLMs. Moreover, fine-tuned, task-specific, lightweight AI models often yield comparable performance to general-purpose foundation models by a small fraction of the computational and energy costs. Recent initiatives, such as the AI Energy Score project, aim to bring transparency to model energy efficiency by benchmarking the energy cost per query across different AI models. Making such metrics available to end users can encourage more responsible usage behaviors and incentivize developers to adopt energy-aware design considerations. And user flexibility and AI demand response. In practice, many end users of AI applications exhibit a degree of flexibility in their usage behaviors as they do not often need immediate AI responses to their queries. For example, a user submitting a complex AI task late at night might not need the results until the following morning. This inherent temporal flexibility and AI demand of end users offers a valuable opportunity to better align query processing with power grid operational needs. Based on this insight, a novel concept termed AI demand response can be developed to harness user-side AI workload flexibility analogous to the electric demand response programs in power systems. Similarly, these can be incentive-based and price-based AI demand response mechanisms. In incentive-based AI demand response programs, end users are incentivized through lower subscription fees, discounted inference rates, or access to premium model tiers in exchange for accepting minor service compromises. Oh yes, that's just what I want. These may include bounded response delays, use of lower-tier hardware, allowing their queries to be processed during periods of low grid stress or high renewable generation. So that's how they're going to screw us. Yay! In contrast, price-based AI demand response programs employ time-varying pricing schemes such as real-time pricing, time of use, critical peak pricing to encourage users to shift their AI usage away from peak hours. I hate this. I mean, I understand some of this for like keeping the grid protected and stuff, but it's one thing I like about our co-op. I don't think they actually do this. I think they're just like, please keep your usage low of the air conditioning so everyone can have air conditioning. Thank you. By exposing end users to dynamic AI usage pricing signals, service providers can influence AI workload patterns in a grid-aware and energy-efficient manner. When aggregating across a large and diverse user base, service providers, AI data centers can provide substantial flexibility to support grid reliability and improve overall cost efficiency. Yeah, that sounds like a great idea. I don't know. Maybe people who are greener than I am think this is a good idea. Anyway, in conclusion, paper focuses on the growing intersection between AI and energy systems, specifically the electricity demand of AI data centers and their impacts on the power grid. It highlights the electricity use of AI data centers is largely driven by computing and cooling loads, with distinct characteristics and patterns across model preparation, training, fine-tuning, and inference stages. From the perspective of the power grid, the large-scale integration of AI data center loads introduces multifaceted challenges across multiple timescales, ranging from long-term planning and interconnection, short-term operation markets, to real-time dynamics and stability. Addressing these challenges requires collaborative, integrated solutions involving grid operators, data centers, and end users, such as advances in AI load forecasting and dynamics modeling, standardization and regulation, grid-aware scheduling, energy-efficient hardware, and energy-conscious AI usage. Looking ahead, the co-development of power grids and AI data centers will be essential to sustain the rapid pace of AI innovation in a reliable and sustainable manner. And then we have an appendix on global AI center electricity demand, which I'm not reading because I know we have already gone way too far. I think that's the only appendix. This all is references. Yeah, it looks like so. Alright, let me know what you guys think. And finding out that thing at the 15-minute mark was quite interesting. So hopefully you made it to the end with me. You can leave a comment.